All right, this video is going to be about some applications for the exponential functions. And we're going to start off with the law of uninhibited growth, or we can use it for uninhibited decay. The formula given is n of t, that's your function notation, equal to n naught, or n sub 0, e to the kt. You'll notice a similarity between that formula and the formula that we used for continuous compounding in the last section, where you have the final amount and the initial amount p, and then e to the rt, where r is the rate of interest and t is the number of years. So we have a similar formula for the law of uninhibited growth or decay. So the first problem will be about bacteria, and we're actually given the formula with the constant k in it. So it looks like this: n of t is equal to 1,000 e to the 0.01 t. Okay. So the constant k here is 0.01 t. In this problem is in hours. And n of t is going to be the number of bacteria in time t. Okay, so we can investigate this a little bit, put in 0 for t, and we'll find that the initial amount, in other words, when time is equal to 0 hours, we have e to the 0.01 times 0. Well, e to the 0 is 1, so the initial amount of bacteria is 1,000 bacteria. If we want to know how much bacteria we would have over after 4 hours, we're going to be looking for n of 4. So 1,000 e to the 0.01 times 4. Okay. And I just plug that into my calculator, and I come out with slightly more than 1,000 bacteria. We've grown to 1,041 bacteria at t equal 4 hours. We can also be asked to find t such that the number of bacteria is 1,700. So let's go over here and say the number of bacteria. Oops. Is 1,700, and we want to find how long it might take to advance from 1,000, our initial amount, to 1,700. So we have 1,700 equal to 1,000 e to the 0.01 t. Divide both sides by 1,000. We'll have 1.7 equal to e to the 0.01 t. We can change that to natural log form. So the natural log of 1.7 is equal to 0.01 t. Dividing by 0.01, t will be equal to the natural log of 1.7 divided by 0.01. And rounding, that will give us approximately 53 hours. The time it takes to go from the starting amount of 1,000 bacteria to a final amount of 1,700 bacteria. Another application of this formula, the law of uninhibited growth, would be a half-life problem. So let's do it over here. We're given certain information about the half-life of radioactive potassium. So radioactive potassium has a half-life of 1.3 billion years. And we can use our formula up here for uninhibited growth, except what will happen is that K, the constant in the exponent, will end up being a negative number. Well, the first thing we have to do is find what is K, find the constant K. And we can use the fact that we have a half-life of 1.3 billion years. So half of our initial material will be gone, or will be left, okay? So half of the initial amount will be what we have after 1.3 billion years, so that's K, the unknown in this particular part of the problem, times 1.3 times 10 to the 9th years. So 1.3 billion is 1.3 times 10 to the 9th. Well, divide by n naught, and then we can change to natural log form once again. The natural log of 1/2 is going to be equal to e to the k power 1.3 times 10 to the 9th. Well, actually, the e is going to be gone at this point, so we're just going to have the natural log of 1/2 equal to that exponent. And then we can divide both sides by the coefficient of k, and it looks like we'll have k equal to 1.3 times, oh, mercy, excuse me, we're going to have k equal to the natural log of 1/2 divided by 1.3 times 10 to the 9th. And I'll just leave it in that form rather than work on a decimal that's been rounded tremendously. Well, that's step one. Once we have found K, we can then use this formula to find what's left after a certain amount of years, or we can find out how long it takes for a certain amount to be decayed. So our question here says, find the number of years until 85% of the original amount, and this is the radioactive potassium, is decayed. Now, if 85% is decayed, that means we have 15% of the original amount. So 0.15 times the original amount, which we'll call n naught, is equal to whatever that was times e to the k t. Now remember, we found k is this decimal number over here. So again, divide by n naught, change it to exponential form. So we'll have the natural log of 0.15 equal to K times T, divide by your constant K that we found over here. We'll have T equal to the natural log of 0.15 divided by this constant that we found in the first step. And when you put this in your calculator, be sure that you've got parentheses around that fraction in the denominator. In fact, you'll have parentheses around the 1/2 also in your calculator. And it turns out to give us a number in scientific notation, 3.56 times 10 to the 9th years. So our conclusion is that 85% of the original amount of radioactive potassium will be decayed after 3.56 times 10 to the 9th years. Okay, another application that we have in this section is called Newton's law of cooling. And it looks like this. U of T is equal to capital T plus U naught minus capital T once again, E to the K T. And when we have that formula given, we know that because we're going to be cooling, the temperature is going to be going down and K will have to be a negative number. And in this case, it certainly will be. Now, U of T is going to be the temperature after time T of our object. T naught is going to be the original temperature of the object. And big T is going to be the temperature of the surrounding environment. So that describes all the parts of this formula. So I've made up some data that we could plug in to find K. Likewise, in that other problem we just did, we had to find K before we could use the formula. So step 1 is to find K. And we're given enough information to do that. We know that the object that's involved has a temperature of 60 degrees. Okay, after 2 minutes, in the refrigerator. And I'll just abbreviate refrigerator, fridge. Okay, so this gives us an initial temperature and amount of time. So we can find K. We also have to know the original temperature. Of the object is 72 degrees. Okay, so plugging into our formula, we know that we have 60 degrees. That's the temperature after 2 minutes. The surrounding temperature is 38 degrees. I guess I didn't tell you that. In the refrigerator. plus the original temperature of the object, which is 72 degrees, minus the temperature in the refrigerator, 38 degrees, e to the k, and we achieve the 60 degrees after 2 minutes. Okay. So we just have to clean this up. I have subtracted the 38 from both sides, and we have 22 equal to adding this or subtracting 72 minus 38 gives me 34, e to the 2k, and divide by 34, we'll have a fraction 11 over 17 equal to e to the 2k. And we can change it to the natural log form. Natural log of 11 over 17 is going to be 2k. And when we divide by 2, we get our value of k that we're looking for. K is the natural log of 11 over 17, all divided by 2. Okay, that turns out to be a negative number because we're taking the log of a number between 0 and 1. So that will be negative decimal. All right, now that we know k, we can use this formula to calculate other types of questions. Let's do it right under here. Suppose we would like to know let's see, how many minutes until the apple is 50 degrees? Okay. I've just been referring to this as an object. Okay, so we want the final amount to be 50 degrees, so that's u of t equal to 50 degrees. And then we can use the information we had over there. The original, the refrigerator was 38 degrees. The original temperature 72. Again, the 38. And e to the k t. K is that constant that we found in step 1. So I can subtract 38 from both sides. And this time I get 12 equal to, and the difference between 72 and 38 is 34. E to the k t, divide by 34, and reduce. 6 over 17 is e to the k t. Change this to the natural log form. The natural log of 6 over 17 is equal to k t. And now we're just going to divide by k, our constant, over in the first step. So let's put it over here. We'll have t then is equal to the natural log of 6 over 17 divided by the natural log of 11 over 17 all over 2. And I'll put that in parentheses just to remind you when you put it in the calculator, you need to put parentheses around this fraction in the denominator. And this rounds up to about 4.8 minutes using the calculator. So the object starts off at a temperature of 72 degrees, and it's going to take 4.8 minutes to get down to a temperature of 50 degrees. Okay, the last example that we wanted to see here as an exponential model is called a logistic model. And in this particular model, we will be given the constant k in the exponent. But it's got some interesting applications. The general formula, let's write what we're talking about here, logistic model. Looks like this. P of t is equal to c, another constant, 1 plus a e to the minus b t. Okay. And in this case, you'll see it's a negative in front of the exponent, but he also says that b is a positive number. So if b is a positive number, actually you're going to end up with a negative in the exponent up here. And t is time. C is called the carrying capacity. And I have an example to do where we're given some information about marketing penetration. Of a certain product. And in his formula for marketing penetration, we have 0.9 as the carrying capacity, and 1 plus 3.5 e to the minus 0.339 t for our exponent there. So all the parts of the formula are given. T is in months. And P is going to be a decimal, which we will change to percentage. When we give our answer. So we want to find the number of months to reach 75% of the market penetration. So that means our final market penetration is 75%, or 0.75 in the formula, equal to 0.9 over 1 plus 3.5 e to the minus 0.339 t. So I'm going to do some algebra. I'm solving for t. I want to get the e term by itself. So first we'll bring that over to the right side. We're just multiplying both sides by our common denominator. And dividing both sides by 0.75. And that turns out to be a nice fraction, 1.2. Subtract 1 from each side to simplify a little bit. Okay, so we subtracted the 1 from this side, subtracted the 1 from that side. Divide by 3.5. And then I can change to the natural log statement. I've isolated e, so we have the natural log of 0.2 over 3.5 equal to minus 0.339 t. And dividing by the coefficient of t gives us a time, which is approximately 339 0.339 gives us a decimal of approximately 8.4 months. So the market penetration of this particular product that we're selling is going to be 75%, okay, and approximately 8.4 months. Okay. I think that's enough of this.